But again, there's something to be said about writing down notes, writing it in your own words so you can keep track, or you make it stick. So we're doing rotation, part 1. I managed to fit these notes into 2 sheets, so if you're trying to predict how much paper you need. All right, let's review a little bit, because we haven't done rotation in a little while. We did a whole energy unit without any rotation in it. First, just redefining right-hand rule. Remember how right-hand rule works? It was if you have this coordinate system, x, y, z, all perpendicular to each other, counterclockwise was positive, so that it would, if you follow the right-hand rule and this turn like this, your thumb pointed in the z direction. I know I draw z down and to the left, but that's actually supposed to indicate that z is coming out of the page. It's supposed to be perpendicular out of the page. So you remember the right-hand rule, you make the L, okay, with your right hand, your thumb is the x, your front finger is the y, and then the middle finger pops up as the z. Don't do it too aggressively. All right. So that if you were to write omega or angular velocity as a vector, the direction of omega is in the z or whatever, in the k direction. It would be sticking out. This is how we can uniquely define rotation, because rotation is always in a plane. Okay. All right. Now going through some of the variables that we used. We had angular position, angular velocity, angular acceleration, theta, omega, and alpha. If you're wondering what this is, I was trying to emphasize that your omega should be really curly at the ends. Merely distinguish it from a W, so it's kind of like the top part of the Batman symbol. Right. So just make sure it's distinct, especially as we get to more variables. W could be work, and you don't want it to be confused for work. Right? Alpha, same thing. Make sure the tails are a little extra long. All right. From there, we talk about some of the translational measurements when something is spinning, the tangential accelerations and velocities. I guess you could call it a tangential position, but I wouldn't. Usually you just see arc length. Right? What's the positional change as it rotates through or distance traveled, I should say, not positional change. Distance traveled as it rotates a certain distance. And then we also talk about centripetal acceleration, right? That is the acceleration inward if it is changing direction, or the acceleration in the direction that is changing direction. We also talk about torque. Torque is a twist. Okay, so a force is a push or a pull. Torque is a twist. You get torque by applying non-collinear forces. So you get a torque by applying forces in opposite directions. Well, I guess it doesn't necessarily have to be opposite directions, but imbalanced, when you have imbalanced forces, right? Okay. These are the new things. We're going to introduce the concept of moment of inertia. Sometimes it's called rotational inertia. I think the AP exam or College Board favors using rotational inertia, whereas in this book, it favors moment of inertia. Same thing. It's the same thing. Okay, we're going to introduce rotational kinetic energy. It's still kinetic energy. It's just we're distinguishing it, we're categorizing it separate from translational kinetic energy. So if something is sliding and spinning, you want to split that energy up into 2 types. Okay. One thing I didn't include on here for the other classes, I forgot. We have to include L is for angular momentum. L is going to be angular momentum. That is a capital L, that is a capital I, capital K.
R-O-T?
K-rot. K-rot. Crot. Yeah, sometimes if you combine the variable with the subscript, you get some interesting words. What do we have? Anyway. Back to it. Okay, so what I want to do is compare the linear version to the rotational version. So, position, angular position, right? Sometimes they ask this question, what is the rotational analog of blah, whatever. So this is kind of how they compare. R goes with theta, V goes with omega, A goes with alpha. And then from here, there aren't any kind of linear versions of these. These are relationships that we created or determined that relate the translational to the rotational. Right, so tangential acceleration is related to angular acceleration by r, and so on and so forth. These are pretty much going to be for circular motion only. When we do gravitation next unit, we'll see that orbits are often elliptical, which means that your radius changes. So sometimes you increase your radius, you have a velocity away from the center. Sometimes you have a velocity towards the center. And so then you can't really apply these exactly as they are. You have to modify them. So just be mindful about that. Centripetal acceleration, pretty much the same thing. This only is for circular motion. At least as it is. There's some pretty easy changes you can make to these to make them work for ellipses, but we'll wait. Ignore this thing on the right for now. So this is, again, for certain, your tangent or your radial acceleration or centripetal acceleration is equal to vt squared over r. When you substitute omega r for vt and you get omega squared r, be careful the units get a little wonky, right? You get these radians that don't show up in your centripetal acceleration. It should just be a meters per square second or some sort of distance per square time. All right. So this one's going to be a little new. What does Newton's second law look like for rotation? Right, so Newton's second law is the sum of the forces gives you the mass times the acceleration, or this is the change in momentum over change in time.
Can you move it down a little?
Oh, sorry.
Thank you.
I just, yeah, that's right. Here. Okay, so then your torque, the sum of your torques around a certain point P will equal to the sum of the forces, or the distance of the applied force from the pivot crossed with the strength of that force, or whatever that force, that force vector. That will result in some moment of inertia times angular acceleration. Okay, so this is like your MA. So if M is like a translational inertia, in other words, it's the resistance to speeding up or slowing down or changing direction to acceleration, then I, or your moment of inertia, is like its resistance to spinning faster or slowing down, changing its rotational speed. You could also argue it's a resistance to changing its rotational direction. Okay, so it can be spinning at 20 revolutions or radians per second, but if it's spinning in one direction and now you're trying to turn it, you're trying to, so like if you have this thing and it's spinning like this, and then you try to turn it like this, it will resist. It will resist. Yep.
So it's like
It's very much how a motorcycle works. On a motorcycle, you have two quite heavy wheels spinning very, very fast. So you don't turn a motorcycle by turning the handlebars. You turn the motorcycle by leaning. And actually, if you try and turn the motorcycle by moving the handlebars, it's actually in reverse. If you want to go to the right, you tend to push to try to turn the wheels to the left. Because, well, we'll get to all that a little later. But changing the directions of a spinning object, it will resist it in a certain way. Okay, it tends to resist it. And so what will really help explain that is recognizing that torques tend to change angular momentum. Okay. What makes it super trippy is, when we talk about applying a force resulting in changing in linear momentum, it's very straightforward because when you push on something, it then wants to go in that direction, right? But rotation is different because how something looks like it's spinning is not the direction in which the angular velocity is or pointing at. So you have to think more about what the direction of angular momentum is, or this angular velocity, not how it looks like it's spinning. It may look like it's spinning up and down, but that means that the angular velocity is like side to side.
So angular momentum also side to side.
Yes, these all follow right-hand rule, all of it. These all follow right-hand rule. So if we go back and we look at this guy, its angular momentum would be out of the page. Okay? All right. Not exactly lastly, okay, just kidding, take it back. So that means that this mass, okay, if you have a linear mass, well, not linear mass, I don't want to describe it as a linear mass, but I guess it's kind of like a translational mass. It's the resistance to translational accelerations. You have this rotational inertia, and the thing is, it's not like this is an entirely separate thing from this. Torque comes from Newton's second law, just taking into account how it ends up working out when you have a rigid body, a two-dimensional or three-dimensional body. A lot of times we do this and we apply it to particles or just some object. We don't care about its volume. We don't care about its shape. When we start having to worry about its shape and size and volume, we end up having to recognize that the forces are applying at different parts of the object. And so this is also actually just a combination of this for all the little pieces of mass that are in your object. So it's not really that moment of inertia is some new physical property. It's not like some fundamental property of an object. The fundamental property of the object is the mass. But when you combine a lot of mass together into some object with volume and space and shape, it's convenient to summarize it in this term we call moment of inertia. Does that make sense? It's like this is a macroscopic measurement that is a consequence of an object having mass stuck together to make its shape. Sometimes we write it like this. You can kind of, for certain shapes, oftentimes they are rotationally symmetric objects, meaning like a cylinder or a sphere. I don't know how to draw a sphere. A cylinder or a sphere, or like a rod that's spinning around here, right? As it spins around, it's kind of rotationally symmetric. Something that's not rotationally symmetric would be like an L. It's kind of hard to describe this for something like that. You can, but it's just not very common. Okay. So, more generally speaking, this is the better description of moment of inertia.
You mean like M initial?
This is, no, so what it is, it's the summation, right?
Mm-hmm.
So it's the ith mass, and its distance from the pivot. Yeah, this is a summation. It's not initial, this is a summation. Yeah.
On the first equation, what's the C?
C is just a constant, and we'll see what you'll see what that is.
What a pun.
Huh?
I'm just kidding.
What constant?
What a pun.
What a pun?
Because it's a C, and you said we'll see.
Oh. Yes.
Yes.
Did that on
I'll
purpose.
see myself.
Okay. All right. So this is squared. That's important. Okay. So it's the sum of all your different objects. Its distance from the pivot. That product, or the square of that distance times the mass, right? And you add it all up. That is your moment of inertia. Something else that we have to keep track of is this. This is measuring the position of your center of mass. Okay, so to measure or determine where your center of mass is essentially a weighted average. So again, you're adding up. You're adding up the mass times the position of an object relative to some origin or some reference point divided by the total mass. So the more mass something has at a certain position, the more weight it will have at that position. Right? This is essentially just a weighted average. So what is a center of mass? Well, a center of mass is the point where an object wants to spin around. If you are in deep space or in space where there's no other forces involved and you just set something spinning, it will favor spinning around a certain point. So for example, if I take this is uneven, right? If I look for the balance point, it's a lot more towards this side than this side. So when I take it and I throw it up and I try to make it spin, it tends to spin around there. It won't spin around some geometric center, right, just because it's long. It wants to spin where it's heavy. So that is essentially what the center of mass is. So you can determine the center of mass this way, because what it's saying then is the torque created here is offsetting the torque created here, so it doesn't rotate relative to this point. So when it starts spinning, another way to think about the center of mass is it's the point that does not move, or that doesn't rotate. It's not spinning, or the point where everything else rotates. The center of mass is also very useful because it, if I throw this up again, everything is moving in like all over the place, but the center of mass is the only one that's actually following the projectile motion because it's not spinning, right? So it follows the projectile motion where everything else is not. So sometimes you'll see this, I think, like in I think that's probably a good enough explanation. Okay, so this is how you determine where it is, and we'll do some calculations of that. We'll also work with kinetic energy. So if kinetic energy in translation, or translational kinetic energy, is 1/2 mv squared, then a rotational kinetic energy is going to be like an 1/2 I omega squared, right? Because I is like the mass, and omega is like the v. That's it. And very similarly, if translational momentum is, or linear momentum is mv, then angular momentum is I omega. This will come up sometimes when you talk about the angular momentum due to a particle, which may seem kind of weird because usually when we talk about angular momentum, you're talking about a rigid body and the whole thing is spinning. But sometimes you want to talk about the angular momentum from a particle as how it is involved in a rotating system.
Why do we have to do the cross product?
It's a cross product. I will explain that later. It's for the same reason why torque is a cross product. Torque is a cross product because you only want the component of the force perpendicular to r, which actually causes it to spin. You only want the part of the momentum that is in the rotational direction of movement. If you have a object just going away from the center radially, it's not contributing to its angular momentum. So it's the twisty part of the momentum. Twisty part.
Really tough points.
Yes. All right. Questions on just setting up the equations? Okay. So let's actually just jump right into applying them. Let's start with calculating center of mass. if you're trying to calculate center of mass for this system, let's say you have a ball over here and a ball over here, you'll find that a lot of times when we talk about discrete particles, or like a bunch of different particles, we like to use spheres. Spheres are nice because they tend to be uniformly distributed mass, and they're symmetric in every direction. And so what ends up happening is you can kind of treat them like all their mass is focused at the center. They act like point masses. So if we have these two and they're half a meter apart, let's say they're held together by a massless rod, then where will their center of mass be? How do you calculate it? You work it out, you get something like that. Pretty much just take the mass, this 2 kilograms. Now, when you do your center of mass, you have to determine ahead of time where you want your origin or your reference frame to be. So if I choose it right here, then this object is half a meter away, and then this object's right at 0. A lot of times, kind of like with torque, you want to choose a spot that is convenient. What makes it convenient? It's going to be a spot where you can determine all the distances very easily. That usually makes a very convenient spot. Either that, or it helps you cancel out one of the calculations and shortens your calculation. Right, so in this case, if I choose this spot to be my origin, then that's right at 0. Makes it easy. The other one is half a meter away, blah, blah, blah. You get, the answer is 0.1. Okay. Now sometimes, when you get these kind of questions on multiple choice, on the multiple choice part, they will often choose values that are very easy to use. Like, they're not going to use 0.87 kilograms and like 0.915 kilograms, nothing like that. What I notice here is that 2 kilograms is 4/5 of the total mass. That's very useful, because that means then that the weight is 4/5 weighted to the left. And you can see that it is at 0.1 out of 0.5 to the left. Right? The more mass it has, the more weight it will pull on the position of the center of mass. How you choose your axis or your coordinate system, whatever, doesn't matter. So if I put it on the other side, let's say I put the origin here on the right hand side, and I make that 0, and I'm measuring x to the left, now you get the center of mass is 0.4 meters, but that's the same spot. It's physically the same spot. For the coordinate system, it's a different value, but it's the same spot. Questions on center of mass calculations? Okay, so if you can do it in the x, then you can do it in both directions. You can do it in the y as well. Okay, so let's say you have 3 objects. This one's 3 kilograms, this one's 5, and this one's 8. Positioned at these coordinates. You just do your sum of the forces relative to 0. Yeah?
So what is the answer to
Or not
that
some forces.
depends depending on where you choose your origin?
It doesn't matter.
Because
The number is different, but 0.1 meters from the left is the same as 0.4 meters from the right. So it's the same spot.
Oh, okay.
Yeah. This answer works for this coordinate system, which is still 0.1 meters from the left.
Okay.
Yeah. So it should not matter. Sorry, I totally said sum of forces. I mean, do your weighted average. There's no sum of forces here. Just do weighted average, right? So this mass times its position. Now, when you do center of mass, you want to break it down kind of like vectors. You just do the components. So you're not looking for the straight line distance. You're not going to do whatever square root of 18 or anything like that. You just want the x component if you're finding the x center mass. So 3 times -3 plus 5 times 3. And then this one's right at 0. Divide by the total mass. And that gives you 3/8. Now the units of center mass is the position, right? So if these were in meters, then your answer would be in meters. If they were in centimeters, it'd be in centimeters. I just did it dimensionless. And then you do it in the y direction. So this is 3 times 3, 5 times 3, and then negative 3 times 8. That ends up being 0. Sometimes, again, if you see these kinds of problems on the multiple choice part, College Board likes to design these problems to be solved sometimes. Sometimes they're meant to be solved. You can solve them very quickly if you're very familiar with the way the equations work out. So in other words, when I'm trying to solve for the x center of mass, I kind of do like a vertical line test. Where are my masses positioned this way, right? So there's the one here, there's one here, there's one here. And then they're weighted, right? If they're all spread out, I would suggest you just use the equation and then you calculate it, kind of longhand. But when I look at it this way, I have two masses here and one mass here. They're really on just two locations. If I think about how they're distributed in the y direction, and I have 8 kilograms up here, and I have 8 kilograms right here. So you can kind of tell that way that the y position is going to be 0. Okay, now that's kind of a shortcut, kind of like how you can do a weighted ratio here as a kind of quick way to do it. If you're not comfortable with doing it that way, just do it the longhand way. This will work every single time. Sometimes you'll see center of mass. The symbol for center of mass is a circle with a cross. You'll see this in a lot of engineering kind of schematics for like diagrams of airplanes, things like that, anything that has to spin. You see this. Sometimes they fill in like this, but not necessarily. Usually a circle with a cross. Okay. So, any questions about calculating center of mass? So this is for discrete points. Most of the problems that I've seen on the multiple choice are discrete points, but on the free response, I've seen a handful. I mean, in the last 20 years of different free response questions, I've seen maybe 2 problems where you need to find the center of mass of a continuous body, a distributed mass, like a bar or a beam, right? Which means that you have not discrete points, but like a distribution of mass. So you have to use calculus. So let's talk about how that works out. What you do is you want to take a slice and represent that slice with a certain amount of mass, dm. Now, if I know you guys haven't done the integral stuff yet, so just think of it like if ever you have a slice of mass, you can always think of it as a thick slice that you will then shrink until it becomes an infinitesimally small slice. You can always do it this way. This is really how integrals work anyway. So you just have this slice of mass that is a certain position x away from your 0, right? You have some reference coordinate system, whatever, it will start at 0. And that is at some position x. And you have a lot of these, right? You have multiple different slices and you go along, and each one has a different value of x. So it is hard to add up these slices of mass because it's hard to know how many of them you have and how spread out they are. So instead, what is more convenient, especially since we're trying to add it up in a direction in terms of x, we want to know how thick they are. We rather use delta x instead of a delta m. We need to convert. So a lot of times these kind of problems will give you something called like a linear mass density, or if you have a sheet, then you're dealing with surface mass density, or if you have a solid, you have a volume mass density. Volume mass density is the one you're probably most familiar with. It's usually written as rho, right? So like rho density, right? Like the density of water is 1 kilogram per cubic meter, right? So this is like volume density, but if you have it uniform and you just have looking at linear slices, then you can talk about a linear mass density. So linear mass density is kind of like how many kilograms are there per meter of stuff, right? So if you want to relate your linear mass density, this is lambda, by the way, that is equal to the amount of mass over that amount of slice, right? If it is uniformly distributed, this should be the same everywhere, no matter what size of slice you have. So if you take the full thing, you have a full 1 kilogram bar, and it's 1 meter long, then its linear mass density is 1 kilogram per meter. So that if you take a tenth of a slice, then it should be 0.1 meters long, and then it should be 0.1 kilograms, and so on and so forth. Right? So we want to use that so that we can relate how our mass is related to our thickness of that slice. And now we take this and we turn it into the calculus version, which is now we shrink that slice into something infinitesimally small. And this equation that we had from before, this one, we're adding up mass times distances. You can write it like this. Okay, those infinitesimally small masses times its position. Be careful not to mix up x and delta x. X is the position of that slice. Delta x is the thickness of that slice. We are choosing a lot of different slices. Those slices are DMs. They're small slices of delta m's, each with its own position x. And we're adding up those products all the way through. That's what the integral does. Okay, and then we're dividing by the total mass. So how do we convert? It's really hard to integrate with respect to dm because we don't really know how the position is as a function of the mass. It's kind of weird to take those kind of slices. What we want is to know where the position is with respect to the thickness of the slice, not the mass of that slice. We want like an x dx. That's kind of what we're aiming for. And so we're going to use lambda, this linear mass density, as a conversion. Okay, we convert our slices of mass into slices of thickness, right? It is worth noting that you can have a linear mass density in the x direction and then a linear mass density in the y direction, depending on how it's distributed, how it's uniform or not uniform, or how it's yeah.
And can linear mass density be like a function?
Yes. So
like
when you get to harder problems, you can have lambda as a function of x. It gets more interesting when lambda is a function of time. Let's say you have a tube of water and it's draining. Right? How's that center of mass? Right? And it drains more on the right-hand side than left or something like that. I don't know. Right? So, but you probably won't run into anything like that for the AP exam. Maybe when you get to college physics. Okay? So then you can translate it into something like this. Now it's like an x dx and a y dy. Now from here, it may seem like you can just do the integral, but I don't want to do that quite yet. Because when you do this, there's a couple things you need to make sure you take into account. First, x is measured by where you put your origin. So sometimes it's convenient to put it on the left, but sometimes it's convenient to put it in the center. For example, what if it's not a rod? What if you have a disc, right? And then you're trying to measure like in all these directions. Okay, so you don't want to do that. Well, that gets interesting in terms of how your linear mass density changes with rings. Right? You can do it that way. Anyway, so what that affects is what x is measured as. Well, then also you have to take into consideration your limits of integration. You have the left-hand side and the right-hand side. If you don't know what I mean by limits of integration because you haven't seen integration at all, basically what it means is you're adding it up from one side to the other, And so if you choose 0 to be on the left-hand side, then you're starting from 0 and you're going to L. But if you start in the center, you're not going from 0 to L, you're going from negative L over 2 to L over 2. Because you're adding it up with different kind of length values. So what this ends up actually calculating out to be, you kind of have to look at the specific problem. So I just leave it like this for now. The best thing to do is if you can always start here and then based on the problem rederive these, because sometimes the assumptions that we made to go from here to here, we kind of assumed that lambda was constant and things like that. So this can be a little tricky. This is probably one of the hard things that can come up on rotation. That's why I put rotation like up here, because this is where we use more calculus than any other units so far. I mean, even work, we don't really use that much calculus. So we will practice some of these problems later. At the least, I'll put it this way, I know that studying for AP exams can sometimes be like balancing which ones you study for, and you just like sometimes have to cut your losses. Like, okay, what minimum can I do to like just get this 5? At the minimum, you should know how to use this one, because this one's pretty easy. The weighted average stuff, that's pretty easy. So you can know how to do this, have no idea how to do any of this, and still get a 5, probably, right? That's the kind of thing. So if you're looking at this, you're like, how do I do this? Don't spend 20 hours trying to figure this out. It's not worth it.
Or we can just study that in calculus and
Right.
apply it.
Well, hopefully, I mean, I really like the idea that if you're taking this class, I hope the things you're learning in this class help what you're doing in calculus, and the things you're doing in calculus help with what you're doing in this class. They're meant to be kind of synergistic. Okay, so we'll deal with a integral case later, but at the least, if you can do this. Any questions on center mass? Or what it is, what it represents? Okay, it's the point where your object's going to want to rotate around. Okay, the next thing we need to talk about is moment of inertia. This thing, moment of inertia. Again, more important, or not more important, but just as important as being able to calculate it, you need to make sure you understand what it represents. In center of mass, you can arbitrarily choose any reference point, and you should still calculate the same moment of inertia, or sorry, same center of mass position. And you have like positive positions, negative positions. You could be above your origin, below your origin, all that stuff, right? This is different. This R is the distance of the point from where it's spinning. There's a really good diagram in here. Okay. R is the distance from where you're spinning, which means that if you spin around different locations, the object has the same center of mass, but if you force it to spin about different axes or axles, it'll have different moments of inertia. So a moment of inertia is specific to where you're spinning it around. So for example, if you look at this, 3 masses attached by rods. If it's spinning around here, and it spins like this, right? This has a certain moment of inertia. And you calculate it like this, mr squared. So you have this 0.25 kilograms. This 0.25 kilograms times its distance squared plus this 0.15 kilograms times this distance squared. And this one's right at the center, so it doesn't matter. Right. And then you get some value for its moment of inertia. If this were spinning around here, and it spun like this, then it would have a different moment of inertia. And if it spun around here, this would have a different moment of inertia, right? So the moment of inertia depends on how far objects are from a pivot point, and you have to specify a certain pivot point. Now, if you have an object that is just has no fixed axle, no fixed point, like I take this thing and I just throw it in the middle of the air, then your moment of inertia will always be around its center of mass. Right? If it's free to spin it's through its natural axis, I suppose you can call it. Sometimes it's called the principal axis. Okay, if it's allowed to spin around its principal axis, then it will go around the center of mass. Principal axes are actually kind of interesting because if you have a three-dimensional object, even though an object may look very symmetric, this may look very rectangular prism-like, the masses inside with the battery and the chip and the camera and all that stuff make it so that the principal axes are not just this way, and this way, right? In other words, if I take my phone, it's really hard to make it spin just like this. It always twists. Right at the end, it always twists. Why does it twist? Because the principal axis is not this way or this way. It's like a little bit off, a little bit tilted, and a little bit tilted because your mass distribution is not uniform, which means that your MR squares are not uniformly distributed, and so it tends to spin it twists. It tends to twist. The other thing to notice about moment of inertia is that it's MR squared. It's the square of the distance. So for an object, two objects of the same mass, the further out I push that mass, or I concentrate that mass, the more moment of inertia it will have. So for example, if I have, these two have the same mass, same weight, right? But this is a solid disk, whereas this is a hoop. And so this has all that mass concentrated out. It's the same radius, right? It's not that it has more radius, it's that each element of mass has more radius. This has all the mass concentrated on the outside. So this is harder to rotate than this one. And we'll look at that in a minute. Okay, so let's just look at how to calculate moment of inertia. Okay, just for practice sake. If we look back at that problem where we found the center of mass, what would be its moment of inertia around that center of mass? Yeah, you just calculate it out. You get something like 0.1 kilogram meter squared. Okay. Questions about how to make the calculations? There doesn't tend to be too much algebra involved around all that little pieces. It's not too often on an AP exam they'll ask you like, oh, if the mass is something and the moment of inertia is something, solve for the distance some third object is away from whatever. Usually you just try and calculate I. But how do we use I? Look at the units, kilogram meter squared. So if you have a certain amount of torque resulting in a certain amount of acceleration, this is kind of how to interpret what it means. 0.1 Newton meters of torque will accelerate 0.1 kilogram meter squared of rotational inertia 1 radian per square second. The same way 1 Newton will accelerate, 0.1 newtons will accelerate 0.1 kilograms 1 meter per square second. Or however you want to, distribute those numbers. But the idea is, just as a force causes an object to speed up or slow down, translationally, a torque causes an object to start rotating faster or slower by a certain whatever that rate per second. Okay? So, in terms of calculating moments of inertia, what we have done here is just discrete points. Discrete points is easy, but what if you have a distributed set of materials? That's, again, where you're going to need to use calculus. The equation looks something like this. I is the integral of r squared dm. So again, you're doing little slices of mass, and you're multiplying by the square of that distance, and then you're adding them all up. Okay, you're adding them all up. Let me see if there's a good model of this. Yeah, there isn't a particularly good diagram. So for now, I'm not too worried about forcing the calculations of the calculus. We'll get to that later. I do want you to look at what the values kind of look like for different shapes. What comes up the most with moment of inertia is the shape. The shape is what determines primarily how big or small your moment of inertia is. Zoom in a little bit. See if you can. So you have these different axes of rotation. Okay, this is 2/3, 2/3, 2/5, 1, and 1/2. So earlier I said it's like a c mr squared. This is the c. This is the c. Same thing here. This is the c. Notice that, like for this one, the b, the length of this doesn't matter because it's not influencing the distance away that mass is from the center. Now, all of these are assuming uniformly distributed mass. The second you don't have uniformly distributed mass, none of this works. You got to do something else. Okay, so what I want you to look at real quick, which ones have the greatest moment of inertia, which one has the least moment of inertia? Greatest is the which? The hoop?
Yeah.
It's just a straight mr squared, right?
Yep.
Which is actually kind of crazy because if you look at the equation, it was just mr squared. So in other words, if I took this hoop and I crumpled it all up into one single ball and swung it on a sling, it would have the same moment of inertia as having all that mass distributed around a hoop. Because the fact that it's in the shape of a hoop doesn't matter. Every element of mass on this hoop is the distance r from the axis of rotation. So it doesn't matter whether it's concentrated in one spot or if it's distributed, it's all a distance r. Okay, so it has the same moment of inertia as one object spinning in a circle. So what you'll notice then, if you compare the disk to the cylinder, or sorry, the hoop to the disk, if you take all that mass on the inside and you push it outward, right? You push it outward and you concentrate it on the edge, you increase your moment of inertia. Same thing is true for the sphere. A sphere that is solid has a lot of mass towards the center too, right? Near the axis of rotation. If you turn it into a spherical shell, again, all that mass in the center gets pushed out. You increase your moment of inertia. Okay? So what does that really influence, having greater or smaller moment of inertia? So if this solid disk has less moment of inertia than this one, not just because, or kind of controlled for by having the same mass and the same radius, right? So this really does have less moment inertia than this one. That means that for a certain torque that I apply to it, let's see. As I apply torque to it, the lower the moment of inertia, the more angular acceleration it should have. The easier it is for it to speed up. So I will demonstrate this. So I take these two and I roll them down a slant. Which one gets down first? Or do they get down at the same time? They're the same mass. Same mass, so like they, actually the mass shouldn't even affect its acceleration, right? So which one gets to the bottom?
Rotation. The one that's going faster, yeah, that's what water.
What do you guys think? Why? What's that? The metal loop? This should get down first? Why? It's not impulse.
Moment of inertia.
Moment of inertia is larger.
So you have a greater torque force.
So I get a greater torque. What determines my torque, do you think? There's two sides to this. There's the force, and then that results in an acceleration. If they have the same mass, they have the same force acting on them, right? If they have the same radius, then they should have the same gravitational lever arm that's causing them to start to roll. So shouldn't the torque on both of them be the same? So then, how do we take into account the moment of inertia? Okay. So think about which one's going to get to the bottom first. Ready? Okay, think about why that is the case. Which one is easier to start to accelerate? Which one's easier to get rolling? The one with less moment of inertia, right? The one with less moment of inertia should be easier to start to spin, start to accelerate. Another way to think about it is when it starts to spin, it must have rotational kinetic energy. It must get that energy from somewhere. And we saw, I didn't really mention it, but rotational kinetic energy is like a 1/2 I. Oops. Yeah, it's like a 1/2 I omega squared, right? So, you know, hidden in here is an alpha, but the greater the I, the more rotational kinetic energy it will have. It's not just that it'll have more rotational kinetic energy. It's more like as it is falling and it's losing gravitational potential energy, right? In other words, gravitational potential energy is transforming into kinetic energy. And as it transforms, it has to transform into translational and rotational. It has to split. The more moment inertia has, the more of that energy has to go into speeding it up or to rotating it than actually getting it going. So really, it's not just the mass, it's not just the radius, it really is the shape. The shape, the size, what that ratio is of converting gravitational potential energy into translational kinetic and rotational kinetic. I'll show you what I mean. So if this has the same mass and same radius, and the shape changed its rate at going down the ramp, then if I have the same shape, but I change the mass and the radius, it should still get down the ramp at the same speed because it should be converting gravitational potential energy into kinetic, the two kinetic energies at the same ratio, because that's the same shape. I'll show you what I mean. Let's say I take a ball like this, and I take a much bigger ball like this.
Oh my god.
Okay. They have essentially the same shape. Okay, we're assuming this is essentially a solid sphere, and this is a solid sphere. Can you catch the bowling ball? Don't worry about the metal one so much. Just make sure this doesn't. So. Put this one on this side so you can see. It's pretty much about the same. And obviously, this is way more massive and bigger. And so you can do this experiment with, well, what if you had a really, really heavy one that was smaller or something like that? It doesn't matter. It's the shape. Okay, the shape is what determines how it transforms the energies into kinetic, translational kinetic or rotational kinetic. Did you want to see it? Did you see it?
No.
Okay.
If you want to do it again, I'll totally watch.
You can do it later.
But I see what you're
Okay. Any questions about moment of inertia how it relates to shape. So one of the things, yep, go ahead. Well, here's the thing. It just depends on where it's getting its energy from, right? If they're both falling the same height, if it has more mass, it has more gravitational potential energy to work with. But the mgh and the 1/2 mv squared, there's m on both sides. So what really matters is the gh. How's the gh turning into that 1/2 v squared? Is it turning into a v squared or is it turning into an omega squared? Right? Is it rotating or is it moving? And so the shape determines that transformation.
So kinetic energy and rotational kinetic energy are two different things.
They are. We'll look at that in just a second. So we'll take a look at that. Actually, let's look at that right now. One of the things that you just gotta make sure you understand conceptually about moment of inertia is, again, because it's dependent on the shape. If you get some question like this, you have a solid, arbitrary shape, right? And it's rotating around a pivot, and you have a shell, right? If the mass is concentrated towards the edges, generally speaking, it's going to have more moment of inertia, right? So without actually having to calculate anything here, you should be able to tell this should have more moment of inertia than this if they have the same mass and size, right? Okay, so how do we work with rotational kinetic energy? There's a couple things that we have to establish first. When you talk about rolling, there's a particular instance of rolling that we work with. Kind of like how there's static friction, kinetic friction. There's a particular case where we look at an object that is rolling without sliding. Okay, so rolling without sliding is like this. At the bottom, at any moment, the point that is contacting the surface is actually stationary at the moment that is touching the surface. Rolling with sliding is like this. That's rolling with sliding. I can change the angle, but it is translating without necessarily being related to the rotation. So when it rolls without sliding, how fast it rolls is going to be directly related to how far it goes. How fast it rolls is directly related to how fast it goes by this relationship. The velocity of the center of mass is equal to omega r. Okay. Obviously, we're dealing with circular objects. So I'm not talking about if you roll an egg or if you roll a jelly bean. I don't know, right? If it's lopsided or this will not necessarily be true. But this should make sense, right? I mean, if it's always making contact with the surface, the distance you travel should be just omega r. What you get is, at the surface here, this is always a stationary point. There's a pretty good diagram of this in the book too. I'll show you. Just a second. Kind of looks like this. Yeah, when you get to look at it in the book, right? As it rolls, what happens around the bottom? Relative to the wheel, the bottom of the wheel is going backwards at omega r, but since the entire object is translating at omega r, then when you put them together, the bottom is pretty much stationary for a second, for a split second. That's how you have, that's how it's not sliding. It has to be stationary at the bottom for that split second. Otherwise, it would be sliding. Okay? Okay, so how do we use this? This is going to be important. There's a lot of problems where you have to take into account whether it's rolling without sliding or if it's rolling with sliding. Rolling with sliding, totally other animal. But if it's rolling without sliding, you can always use this.
That's what happens when you ask.
Yeah, if it's rolling with sliding, that's a significantly harder problem. So we'll deal with that a little later.
Oh, we do deal with it.
Yes, there has been AP problems that involve sliding. Okay, so when you talk about kinetic energy, and we split it into a rotational kinetic energy or a translational kinetic energy, you can talk about the kinetic energy of rotation and the kinetic energy of the center of mass. Because again, we said the center of mass is where it's not rotating at all, right? So if you do have an object that is just falling down or rolling down a hill or a slant of some height h at some angle theta, what determines how fast it's going at the bottom, right? Or pretty much if it's going faster, then it probably got to the bottom faster, right? Well, let's look at the conservation of energy here. Your gravitational potential energy has to turn into one of those. And if it is rolling without slipping, we can make this substitution. Right? If it is rolling without slipping, there is a constraint on how fast it can move and rotate. Or they're connected. They're related, right? So my omega is VCM over R. You use capital R to stay consistent with the book. But what you can end up seeing is that a lot of things start to cancel out. Okay, so again, this is the rotational kinetic energy. The rotational kinetic energy, translational. Rotational, I start substituting for whatever the shape is, some sort of CM R squared. That R squared is going to cancel with this R squared from the omega. We find that the translational velocity, when you do all the algebra, is actually turns out to be something like this. Okay, so this is kind of how you can apply rotational kinetic energy. Essentially, what using rotational kinetic energy does is you now have another spot for energy to go to. Whereas before it was like either you gain kinetic energy or you gain potential energy. You now, when you gain kinetic energy, maybe some of it is rotational and some of it is translational. The same way potential energy could be like maybe some of it's gravitational, some of it is spring, right? You have these different slots where your energy can go. Rotational energy is like another slot. Okay, so if you work through the math and you get to this conclusion, as an object rolls down a ramp, and here we're assuming there's no losses to friction or anything like that. It's not sliding. Your velocity is the square root of 2gh over c plus 1. If it was just free fall, if it was just a particle, we're used to square root of 2gh. Square root of 2gh is something that's come up a lot. It's how fast an object goes when it's in free fall. That should make sense because if it is a particle and it cannot spin, then c is 0, and you have 2gh over 1, which is just 2gh. But what if it can spin? What if it's like, here's some of the ones we had. You know, what if it's like a hoop or like a disc, right? The disc has this 1/2 c, which means that you would have like 2gh over 3/2. Or if it's all the way to just mr squared, it's just mr squared, the coefficient here is 1, c is 1. So then this becomes like a 2gh over 2, or just the square root of gh. In other words, its translational velocity will decrease, maxing out at square root of 2gh and at a minimum square root of gh. I don't think you'll really see this, like you don't have to memorize this. And you don't really have to memorize this either.
They can be equal to, right?
Yeah, or equal to, yeah. Or equal to, you're right. The idea here is that you lose translational speed when you start having to spin. Spinning always removes energy away from your ability to translate. This also means that the more moment of inertia you have, the more energy has to go into causing it to spin as it tries to translate. Right? So this is a more mathematical explanation for what we just saw with the disc and the hoop. But it's good to describe it both quantitatively and qualitatively. Okay. Questions about how to use kinetic energy in calculations or rotational kinetic energy? It's just like an extra one. This is the complete kinetic energy. Yeah, both. That's it. Okay, the last thing I want to address is angular momentum. Now, angular momentum is probably something that you guys have seen pretty commonly, to be honest. All seen this, right? I take my spinny chair, take my legs out, I spin, and I bring my legs in, and I spin faster. That's conservation of angular momentum, right? Angular momentum L equals to I omega. When I stick my legs out, I have a higher I bring my legs in, I have a lower I, but I have to maintain my angular momentum, so my omega goes up. Or vice versa, right? So that's like the ice skater effect, right? Why is it when they pull their arms in, they spin really fast? Why is it that if you ever want to try and do a back tuck, you do jump and do a backflip, you pull your legs in, so you can spin faster. It's the same idea. There's a lot more subtle things to angular momentum than this. Another thing that you really need to keep track of, let's actually talk about these vectors. L is a vector, right? So let's look at this equation here, this one. I'll put this on the side of it. This. Tau, my torque, results in a change in my angular momentum, right? So usually, when we talk about linear stuff, I think it's really easy to see how an acceleration changes the direction of my momentum, right? If I'm going straight and my momentum's this way and I accelerate to the left, then I should turn to the left. But when you talk about this, if I have a certain angular momentum in a certain direction, and I have a torque in a certain direction, my angular momentum should shift towards my torque direction. This leads to some really trippy behaviors. So, let's say I take this wheel and I start spinning it this way. What direction is my angular momentum? This way. Okay. If I hold this string here and I let it go, which direction is the torque due to gravity?
Oh my goodness.
Which direction is the torque due to gravity? Which way is it rotating?
It's coming towards us.
The torque is towards you because it is R cross F. F is down, R is this way. R is the distance from the pivot point to the application of the force. Okay, so torque is towards you. Angular momentum was this way. So torque is going to try and turn the angular momentum towards you. Notice that it keeps rotating though because the torque is constantly 90 degrees out of phase of the direction of the angular momentum. Right? When it's going like this, angular momentum's this way, and it wants to fall, so torque is towards you. But as it turns, Now it wants to fall like this, torque is that way, angular momentum is that way, so it wants to
Just keep going.
yeah, it keeps wanting to go. So there's this interesting effect about how, when it comes to rotating objects, your torque tends to be 90 degrees out of phase of your angular momentum. And so that means that whenever you apply a torque, it always wants to turn towards, again, where you apply the torque. So if you start spinning it, again, when I try and rotate it this, like this, it wants to turn right. It's weird. Okay, if I try to make it turn right, it wants to flip over. That is
Wait,
gyroscopic precession. Okay,
so if you want to turn left, you actually turn right.
it's not quite like that. It's more like if I wanted to go right, that means, think about what that torque is. That means I want a torque that is down. Or no, wait. No, if I want to turn right, sorry, that's right. If I want to turn right, then I need to apply a torque that is facing you. Right? Okay.
So you need to.
So I need to, so I don't, in other words, I don't want to force it like this. I want to do this to make it do this, which is super weird. But that's gyroscopic precession. That is essentially what gyroscopic precession is. It is that a rotation, when something is spinning, its current state of angular momentum makes it
That means if you want to go like this, you twist it like this, so that it goes like
react oddly to torque. Okay, so
basically it's wheels that don't actually
wait,
grab.
one last thing. Okay, so if I have conservation of angular momentum then, okay, and I get the spinning, right? Right now there's a certain angular momentum, it's facing down. Me and this wheel as a system have a current angular momentum down, so I go like this. What does it do to me? What's it doing to me? Right?
What? Oh, it's because of the acceleration.
Because as I apply a torque on it, it applies a torque on me. This is the third law.
Okay.